All right. Good afternoon, everyone, and welcome to the final UniKORN seminar of the year. We're very excited to welcome Gabriel Hetet and James Millen, who will be chairing this session. But before I get on to them, there's a few quick announcements and reminders. Of course, simple house rules. I guess you're all tired of hearing it, but just for any newcomers, please mute yourself and your video if you can to save bandwidth, and also questions if you're joining us on Zoom will be at the end by just simply raising your hand, or you can ask in the chat. And if you're here on YouTube, then please feel free to write your questions in the live chat, and we'll pass them on to the chair to ask them at the end. Now, let me first introduce our chair. It's Dr. James Millen, who is a senior lecturer at King's College London, and we're grateful to have him. He did his PhD in atomic physics, actually, as it happens, back in some time, and from Durham, and then joined Peter Barker's group at UCL to start his adventures in levitated systems, and then with the Marie Curie went over to Vienna. And then only a few years ago, he started his own group at King's here. So without further ado, let me pass it over to James to introduce our guest speaker today. James, it's all yours.
Great, thank you, Madassa. Yeah, so it's a real pleasure to have Gabriel Hetet here today. Before I start introducing Gabriel, I would like to say, since it's the last seminar of the year, thank you so much to the organizer of the UniKORN seminars. They've been even better than we imagined, and it's a really impressive effort, and I think we've all enjoyed it. Please give them feedback if you get the opportunity. Here I am introducing Gabriel Hetet, who is from Laboratoire Pierre Agrin, at the ENS. And in fact, so these introductions are a bit long and sprawling for our invited speakers. So, and we have many junior researchers join these calls, so I hope you don't mind if we have a bit of an informal discussion, Gabriel. And I thought that because I find it so hard to even understand exactly where you work, perhaps you could start off by telling us a little bit about how a career in French academia works.
Yeah, so it's in French academia, you have a very specific situation where young researchers can have permanent positions. I guess this is something that's quite rare and unique, and that's the most significant difference, I would say. So, of course, this has consequences in the way we run experiments, for instance, because I'm an experimentalist, so I really know how it works there. And compared to most groups in Europe, I guess they are quite tiny teams of a few 4 or 5 people in general. So that, I guess, is the main difference. And yeah, plus the fact that we have these permanent positions. Also, the students, at least in my institution at École Normale, there's this grande école system, where the best students get grants and they're being paid during their studies as well. So this is something that's also quite rare in Europe.
And do you get as a junior researcher who has a permanent position, do you get research independence, or are you under a director?
This also is, this varies a lot from one group to the other. I guess I'm quite independent, I would say. I think it's the majority of young researchers that they get to put together their own labs. It depends a lot on the kind of research you're doing, but in optics, in general, the labs are, you can run decent experiments, so to say, on a 50 meters square, even less, with an optical table and being quite independent. It's not like a huge consortium, or you're not building gravitational wave detectors. So it's quite possible to be independent quite soon. And at least at École Normale, you you have this chance to be able to start with this opportunity. Yeah.
I mean, that's very interesting. All the different systems around the world, I think, are interesting.
Yeah.
But I have to ask you about some science now. So if I'm right, you started your career in trapped ions. Is that correct?
No, my career, yes. But my PhD was on atomic physics so quantum optics with atomic vapors, where we did store light in atomic vapors, and then I moved to Innsbruck to do trapped ion physics as a postdoc. Yes, so I started a bit like you on atomic physics, and then moved on to this levitation.
Well, this wasn't actually in my questioning, but that makes me curious. So, what skills do you think you learned from atomic physics that have been useful for you in this levitated optomechanics field?
Well, it's, I guess, not. What I learned from atomic physics is I could directly use it to understand rather quickly, let's say, the physics of nitrogen-vacancy centers, which is the impurity that I will talk about in a few minutes. So, but yeah.
I always find if I get asked a similar question, I come at it from the other direction, which is the terrible habits I got from atomic physics. For example, the belief that levitated nanoparticles were just big atoms with a larger polarizability. But perhaps actually that inspired your research moving to working with ion traps as well, which overcomes in some way the challenges of working with these somewhat messy chunks of diamond, right? Kind of can just ignore that and then just throw it all into the charge to mass ratio and not have to worry about polarizability and optical absorption. So then was it natural for you to have this idea of working with the levitated nanodiamond? Did that clearly lead from your kind of academic story up to that point, or was it a bit of a jump to something different?
It was a smooth transition, yes, because as you said, I was always working with trapped ions, and then I actually did another postdoc in Cachan in the south of Paris, where I worked with nitrogen vacancy centers coupled to nuclear spins, and this was on fixed diamonds. And so then it was natural to combine these two technologies to do these experiments that actually started with a student of mine who's now a postdoc, Tom Delors, and we started doing this experiment for teaching purposes to try and build a little experiment that we could run in. Of course, there's a lot of high voltage and so on But in the end, we were waiting for a cryostat, and it took a bit of time to come. So then we spent a lot of time on this little tabletop experiment, which grew over time, and so it was not,
So from my point of view, I started in this field in 2011, and I remember when the first results started coming out of your group. They seemed to come out of nowhere and very fast, and you've done really beautiful work and very important work. Do you feel that having a small team helped you be flexible and kind of rapid to respond to new ideas and try new stuff out and experiment on the ground? Because I do feel that it's an experiment that got started very, very quickly. Maybe you feel differently.
It was a lot of surprise. So I'm not sure. From our perspective, it didn't feel like it was fast. It was more really a lot of fun. But I don't know if having only a few students helps in terms of, probably it helps in terms of flexibility. That's for sure.
It certainly is a fun field, the working with these levitated objects. It's frustrating at times, but certainly fun. That's another bad habit I learned in atomic physics. Is in atomic physics, you can always find a paper on any problem you have. But that's not true in levitated physics. It's all new. Okay, so we should get on with the talk, but I'm going to ask you one last very quick question, which you'll probably cover in your talk anyway. What is your dream result that you would see from your experiment? What is, if time was not an object, what do you feel this experiment is going towards?
Well, I'm going to talk about this in my first slides. I guess the general motivation for our work. It's more, it's a dream. It's not something that we really think we're going to do, but
then I'll leave it to your talk. So thank you very much, Gabriel, for that very unprepared and informal talk. And so it's with great pleasure that we're going to hear this talk about spin control of levitating nanodiamonds. And I hand over to you if you just want to share your screen.
Yeah.
Looks good. Perfect. All right. And I hand over to you. The floor is yours.
Thank you very much, James. And thanks also to the organizers for giving me this chance to speak today. I'm very happy to present to you the first, I will give you a broad introduction to the field and also show you our recent experimental results. But I'm having trouble to, that's fine. So I will speak to you today about spin mechanics with levitating diamonds. I hope the sound is okay. Just make sure that it'll. I would like to have some feedback at some faces, and I don't see any. Oh, that's it. Okay. Right. Sorry for this. I will be talking to you about our latest experiment where we have, as you see on this picture, levitating diamond and a few nitrogen vacancy setters inside that we use to control the motion of this diamond. And I cannot pass my slides. So what's wrong? Right. What's going on here? So before showing to you our experimental results, I would like to acknowledge the work of my collaborators. So that's an old picture of the team where you see Maxime Perdria, Clément Pellet-Marie, who are the two new students in the team, the new PhD students. And there's also Paul Huillery, who's a former postdoc, and Tom Delors, who worked also intensively on the experiments I'm going to talk to you about today. We have collaborations with Alexandre Thaler, Vianney Emile, and Jocelyn Achard from the University of Villetaneuse, who help us with.
I can't see the slides, Gabriel. Sorry.
Yeah, I'm not sure what's going on. Should share the screen again. Oops. Is that okay now?
Yeah, that's it.
Yes.
Okay, and what about now?
Yeah, that's good.
All right.
That's perfect. Thank you.
Sorry for this. And we recently started a collaboration with Oriol Romero-Izard from Innsbruck and Ben Stickler also on the physics of these fully rotating nanodiamonds in the presence of a magnetic field. And so that's the outline of my presentation today. I will give you a very short overview of the field of spin mechanics with AV centers, and then I will show you our latest experimental results on spin torque and spin cooling, as well as dipole-dipole enhanced mechanical rotation, which are results that we obtained a few months ago. All right, so I guess to answer James' question, one of the motivation for many people and for us, it will be to really enter the quantum regime where a single spin can talk to a mechanical oscillator that can be here represented by this discrete eigenstates of the harmonic oscillator, which are phonon Fock states. And once you are able to get a single spin to act on the mechanical oscillator and the mechanical oscillator to also act on the spin in the so-called strong coupling regime, then it will be possible then to envision really crazy experiments where you'd have, for instance, that's an experimental setting here where a little cantilever, which has a magnet at the very edge, can be coupled to a spin. And so you could imagine that if the magnet if the spin is pointing up, then the magnet will be attracted to the spin. If the spin is pointing down, it will be repelled, and therefore you have this coupling going on. And one of the crazy things you could imagine doing then is to prepare the spin in a coherent superposition of the spin being either up or down, and then you would get the mechanical oscillator to also being in a coherent superposition. So that's a really genuine Schrödinger cat state. And that really is a possibility that motivates many researchers, including us. It's really, really difficult to do because of all the many degrees of freedom involved in this interaction. But one could imagine to do baby steps on the way and try to observe this interaction with the many degrees of freedom to try and understand better what's going on there. And the workhorse of our experiments, at least with regards to the spin part, is the negatively charged nitrogen vacancy center, and specifically its electronic spin. So if one considers the two unpaired electrons of the nitrogen vacancy center in the ground state, they will actually interact through dipole-dipole interaction, these two electrons, and this gives rise to a natural quantization axis along the NV direction. So this dipole-dipole interaction lifts the degeneracy between the ms equals 0 and ms equals plus or minus 1 states of this spin triplet by about 2.87 gigahertz at room temperature. And the very important thing about the nitrogen vacancy center is that you can really manipulate its spin at ambient conditions. The reason for this is that you can do optical pumping in ms equals 0 state using really simple green laser. For instance, you'll be able to polarize the spin in ms equals 0 state due to an intersystem crossing in the optically excited state. I don't have time to explain to you how it works, but it's really kind of magic that it works so nicely, and that's very, very rare for a solid state spin. And the other important property is that the photoluminescence in the infrared that you will get when you shine green light is proportional. The count rate that you will get is proportional to the probability of being either in the 0 state or in the plus or minus 1 state. So that there's going to be many more photons once you're in the 0 state than if you're in the plus or minus 1 state. Meaning that when you scan a microwave about the 0 to plus minus 1 transition, you will see a drop of the photoluminescence at 2.87 gigahertz. And now, if you apply a magnetic field that is not along the NV direction, for instance, then you will mix the three states together. So the 0 state becomes a state that is a little magnetized, and you have dressed sort of states, which are and the energy of which will depend upon, of course, the magnetic field amplitude, but also the angle with respect to the B field. And this is due to this magnetic dipole-dipole interaction that you see here at the bottom, this h bar d sz square term, which means that the energy transition will depend upon the angle between the B field and the NV axis. And so for us, it's really the key point, because we can then think about exerting a torque on the diamond, because you see the slope of the transition energy with respect to the angle gives rise to when you have a lot of spins, a significant torque acting on the diamond. And so there has been many experiments that investigated the coupling between the nitrogen vacancy center and the motion of objects, the center of mass motion of a cantilever, for instance. So here I listed four papers where the spin of the nitrogen vacancy center was used to read out the motion of an object. It can be either a clamped oscillator, such as this cantilever here, or a levitating particle. So in this experimental curve I showed here at the top, you see a modulation of the spin echo signal when a magnetized cantilever undergoes Brownian motion on this very close to a shallow NV center in the diamond. This was an experiment that was done in 2000. So I cannot see the year. 2011, in a group of Michael Lukin, and there are also other experiments that looked at using the mechanics to control the spin. So there is an interaction. So the strain in the mechanical oscillator can drive the two spin states, the plus and minus 1 states, and then you can observe Rabi oscillations by driving the cantilever at the mechanical oscillator frequency. And in our experiment, what we do is to couple the spin and the mechanics in a way that, as I said, the spin can exert a torque on the diamond, as well as, and the mechanics can also exert a change in the spin state in the presence of a microwave. And I will explain to you all this. The major difference also is that we use many spins, like 10 to the 9 in our present experiment. And I will explain to you these two experiments that are listed here, the spin torque and spin cooling, as well as the dipole-dipole enhanced mechanical rotation. But a few words on our experimental platform first. So we use a pole trap, which many other researchers are also looking at this platform, because it actually ends up being quite non-invasive. The electric field from the pole trap doesn't perturb too much the spin properties of the nitrogen vacancy centers, as opposed to optical tweezers, which under vacuum have the disadvantage of really heating up the diamond significantly. And so this somehow increases the number of non-radiative channels and ruins the spin polarization and the low vacuum. It's also the case in our experiment, but under 10 to the minus 2 millibars as opposed to a 1 millibar in optical tweezers. So we can have, there are some significant improvements in principle with respect to the quality factor. So these are the few numbers. You can see we use the pole trap, which is very, very tiny. It's 200 microns. Trap voltages in 2000 volts peak to peak. And we have surface charges, which are electrons. Of course, we need those to confine the diamond in a pole trap. As you see, we have diamonds which are really, really heavily doped. They contain 10 to the 9 spins, and so they are really pink. And this means that we, of course, going to have all the possible NV center directions in the crystalline structure of diamond. And so when we run a so-called ODMR, so optically detected magnetic resonance, really as the one I showed before, instead of observing 2 lines, we see 8 lines, from the 0 to plus or minus 1 states times 4, because of the 4 NV center directions. So this plot on the top right was obtained. My mouse doesn't work, I guess. Right, sorry for that. Was obtained with a diamond that is levitating, and it is very similar to the kinds of ODMR spectra we obtain when the diamonds are outside the trap, meaning that the T2 time, the T2 star time, is not significantly impacted by the pole trap, and also that the diamonds are angularly stable. Otherwise, of course, the lines would be shifting about, and the width of each of these lines would be increased. Another important quantity, especially for the spin cooling experiments I would like to talk to you about next, is the relaxation time, or the T1 time, the longitudinal decay of the diagonal terms of the density matrix. So it's quantifying the time it takes for the population from the 0 state, for instance, to be transferred to the plus or minus 1 state. In our experiments, at least in dilute samples, it is fairly long. You can see here in this plot where we shine 2 laser pulses and then vary the time between the 2 laser pulses to measure how long it takes for the population to be transferred to the plus minus 1 states, starting from the polarized 0 state. And takes a few milliseconds. In heavily doped samples, it gets much shorter, and I will come back to this in my last part. Okay, so this was about the spin properties. And now I'd like to say a few words about the librational modes. So libration is a word which describes angular oscillation of a diamond about its mean equilibrium position. You can see here a little GIF that shows the oscillation about one direction. So it is a harmonic oscillator, and it can take place in principle about the 3 main axes. So you see at the bottom an SEM image of our diamonds, and quite fortunately they are asymmetrical, which means that in the trap it's quite likely that we are going to have an angular confinement, meaning that under vacuum there's going to be some collisions with the gas particles, and there will be a libration at particular frequencies given by the particle shape and the pole trap shape as well. And so we built an experiment to try and really measure these librations, And the very important ingredient that we use is the speckle pattern that is formed in the image plane of this confocal microscope that is shown here. And this speckle comes from the fact that we have a rough diamond surface and that we use a coherent laser source. So there's going to be multiple interference between the various paths being reflected off the diamond surface, which gives rise to this speckle pattern. So in a way, yeah, we are really exploiting the full imperfections of our diamonds, the roughness and the asymmetrical shape to both have a readout and a stable libration. Because yeah, we pick one particular point in this speckle pattern on the slope of this fringe, and then inject it into a single mode fiber. And then when we do the Fourier transform using a spectrum analyzer of the time trace we obtain, it's amplitude modulation that we observe on the APD, and we see these three peaks, which are in this particular instance go from 400 to 800 hertz, meaning that we really have a stable libration. And we can check that these peaks are really librations and not center of mass motion by driving the spins. And yeah, this is actually what I will show you now, how we drive the spins and what consequence it has on the libration. Yeah, so if we, of course, now imagine that we apply a magnetic field. You see on the top left, if we apply a B field, then the NV center direction is changing when it librates, and therefore the projection of the B field onto the NV axis changes over time. And then if we apply a microwave, then we'll be able to read this out. And that's the principle of the readout that I just talked to you about. Okay, and then now we'll discuss these 2 points I advertised initially, the spin cooling experiment, and next the dipole-dipole enhanced mechanical rotation. Okay, so as I said, one of the many ingredients that we use, and what we got us really excited initially, is to imagine that we could use the nitrogen-vacancy centers to operate the diamond as a compass, right? So it's possible because the T1 time is so long, and then we can repolarize the spins, use a microwave to drive the spins in one of these ms equals +1, 0, or -1 states. And so in principle, if we are in a +1 electronic spin state, then the diamond will turn it will turn clockwise if the B field is pointing downwards, meaning that if we place then the single mode fiber that I just talked about, in this speckle pattern, in this particular direction, then there's going to be more light than if we are in a -1 state, which then will tend to rotate the diamond clockwise. And so we tried to do this experiment, and the first thing we measured, of course, is the ODMR. So looking at the photoluminescence as a function of a microwave frequency, we see these 8 peaks in this heavily doped sample from Adamas, actually. And zooming on the second peak and on the on this ms equals 0 to -1 transition, and on the ms equals +1 transition for a particular orientation of the nitrogen vacancy center, we can there at the same time record the scattered field from the diamond surface. And what we were very happy to observe is that indeed it corresponds to the cartoon I just discussed, right? So there is more light when we are in a +1 state, sorry, than if we are in a -1 state. So the diamond really turns to minimize or maximize the scattered field. So we have this magnetically detected magnetic resonance, MDMR, setup now, which enables us to, in a quite efficient way, I should say, it takes a few seconds to have a scan that looks a bit like this one. So we have very good signal to noise ratio. Of course, we have 10 to the 9 NVs. So this is the reason why that there's a strong and a very tiny particle as well, with a small moment of inertia, meaning we're very sensitive to the spin torque. And this is now the full image, where the full spectrum, where we see that there's an alternation of the spin torque directions as we go from one NV center class to another. And yeah, we were happy to observe the spin torque, but then we thought perhaps there is a way to also cool the motion, because after all, we are, this is done under vacuum, so there's very little energy exchange. And at the same time, there's a possibility to tune the time it takes to magnetize the NV centers. So once, so if there is a delay between the magnetization, which then induces a delayed spin torque with respect to the pole trap torque, then there is a possibility to have non-conserving spin torque. And then in the end, we can think about cooling or heating up the motion. So I'm not going to have much time to explain this to you, but the very simple picture to bear in mind is that we can, by driving a microwave to the blue, we can absorb a librational phonon, and then this absorbed energy can be re-emitted in the form of phonons. The kinetic energy of the photons, is then extracting the heat, and at the same time cooling the diamond libration. And if we drive the microwave on the blue side, then we can scatter off librational phonons and heat up the motion. And we've done this experiment by looking at the power spectral density for two librational modes here. And we see that indeed, when we drive the microwave on the red side, because of this spin mechanical coupling that is strong enough, and because of this little delay between the spin torque and pole trap, we see a significant reduction of the area below the peak. When we drive it to the blue side, instead, we see an increase in the area below the power spectral density peak for two librational modes. So putting some numbers down, we get cooling rates that are by a factor of 4. And this means that we go from 300K, if we assume that we are at 300K, thermal equilibrium with the gas particles, we go from 300K to 80K, thereabouts. So the limits of this cooling is essentially the fact that we have at the same time red and blue detune excitations. So there is a competition between the two processes, which would no longer be the case if we were in a ground state cooling limit, where the trapping frequency, omega phi, was much greater than the decoherence rate given by the coupling to magnetic spin path given by the substitutional nitrogen vacancy centers. Substitutional nitrogen atoms. So we are really not in the sideband resolve regime, and we are hoping to be there by putting together this setup here that is shown on the top left. So we have in mind the setup where we have a diamond nanopyramid at the edge of which we would place a nitrogen vacancy center or a few nitrogen vacancy centers in a CVD grown sample in order to have line widths that are in the range of hundreds of kilohertz. And this is something that is possible to achieve. And then we would levitate a magnet instead of levitating the diamond. So it's really the opposite situation, but the physics is very similar. And we would employ the high librational frequency that can be reached using soft magnets, for instance. And in fact, we've done experiments where we see that the quality factor is very large, and the librational frequency can reach above hundreds of kilohertz, and the magnetic fields of about 800 Gauss, right? So you see, this is enabling us, in principle, at least, to enter the sideband resolve regime. Now the question is how difficult it will be to bring this diamond nanopyramid close to the magnet to have a sizable coupling between the two. So not only would the magnet have to change the Zeeman effect on the nitrogen vacancy center, but also the nitrogen vacancy center must apply a significant torque or a significant force to the magnet in order to be able to have this cooling effect happening in the sideband resolve regime. All right, so this was about the first part of my talk. I will now move on to more recent experiments. So I'm not so sure if at this point you would like to have questions, or should I continue on?
Gabriel, we normally continue till the end, and then we can.
Okay. How much time have I got left, if I may ask?
About 15-20 minutes.
Okay. Yeah. So this is now a new experiment which exploits the fact that in our heavily doped samples we have dipolar interactions, and we've seen this in experiments, where we did not intend to look at it in a levitating platform, but we've seen that these processes are quite strong, and this is also has been seen by many groups. When you get to concentrations above 5 ppm in diamond samples, you start to really see dipolar interactions taking place, and we have used it in the levitation configuration to try and observe its influence on the motion. So we'll talk to you first about how to observe dipolar interactions in diamonds that are fixed, not levitating, and then move on to our kind of novel understanding of the diamond paramagnetic susceptibility, and then put the two together. So how does the dipolar interaction impact the NV center diamond paramagnetic susceptibility? Right, so we are interested in this not only because we, as I said, we've observed this effect in the lab next door, but also because, of course, yeah, the interplay between dipolar interactions and mechanical oscillators, it's a topic that has been looked at for many decades. And I guess the most well-known physical processes is when you have dilute samples, so non-sample of spins that do not talk to each other, and they are coupled to a mechanical oscillator. And in this process, actually, it turns out if you do things right, I mean, it's low decoherence and enough spins, and you can run into actually a phase transition. So there is a mechanically assisted para-ferro transition that can take place very similarly to what you would get if you had a collection of spins, diluted ensemble, coupled to a bosonic bath, which would be photons. In our case here, it's a mechanical oscillator. It's actually well known that in this situation, you would have a quantum phase transition, which is predicted in the Dickey model, where you'd have a normal states, which would be either, paramagnetic from a state which is a super radiant, where you'd have all the spins that point in the same direction and would undergo a ferromagnetic transition. I cannot pass mass. Oh yeah. And so in our situation, it is, as I said, different. I mean, it's been also looked at, but I would say less intensively. And what we have instead of this dilute ensemble coupled to the mechanics is atoms that are already dipolar coupled significantly. And we were interested in seeing whether it's possible to have an effect directly on the mechanics. The question we ask ourselves is whether the fact that the spins are already interacting can have really some influence on the motion in our experiments. And it turns out that this has also been, as I said, looked at recently, because if you have a collection of dipolar interacting spins already in the optical dipoles that talking to each other, this can cooperatively enhance the optical dipole force. And this was looked at in these two papers, theory and experimentally. Even in the presence of global dephasing, this can take place. In our experiment, we look at the influence of the magnetic dipolar interaction and not optical, and also look at the spin torque it induces. And also the difference also is, as I will explain, is not related to the fact that we have spin flop processes that can that are mediated by the exchange of photons, but rather a cross relaxation process that takes place due to the fact that some spins in the sample have a different T1 time. Okay, so indeed in our sample, as I said, so these are heavily doped samples, so the dipolar interactions take place. They are there. I mean, but the coupling strength is in a range of hundreds of kilohertz. And the reason why we see those is similarly to this paper that is shown on the top here, is that we have in the sample some nitrogen vacancy centers that have a short T1 time. And when you are in this situation, you'd have for, let's say, nitrogen vacancy centers of a given orientation. Remember, we have 4 different classes of NV centers, but if we pick only one particular orientation of NV centers, some nitrogen vacancy centers will have a long T1, and some others will have a short T1. the reason why it is the case is that it's under debate, but there seem to be charge tunneling between some nitrogen vacancy centers and other defects, which bring about dephasing or relaxation in the dark, actually. So now we have these two classes of NVs, NV1, which are bright, polarized in the zero state, and NV2, which are dark because the T1 time is much shorter than the polarization rate of the laser. And if we then couple these two kinds of spins together, then the lack of polarization of the nitrogen vacancy number 2 is going to be transferred to the nitrogen vacancy number 1, right? So in a way, the nitrogen vacancy that was bright becomes dark when it couples through dipolar interaction to the spins that are depolarized due to this, probably to this charge tunneling effect with other impurities in the diamond. Okay, so what you have to remember is that this dipolar interaction is really making the photoluminescence drop when we reach this resonance condition. So how can we tune this, and how can we be sure that this is really taking place in our experiment? Well, it's actually quite simple in practice, because if we take an ODMR, and so this is really the same sort of spectra I showed before. In general, we have 8 lines. But if we tune the B field in a clever way, both in its angle and its amplitude, there is a possibility to merge 2 classes of NV centers to a single line. And when this is happening, the density of the resonant electronic spins is enhanced, right? So the effective mean distance between the resonant spins is really reduced, meaning that the dipolar interaction should increase. And this will in principle, enhance the cross-relaxation effect I was talking to you about a slide ago. So it's not possible to see in this experiment on this slide that cross-relaxation is happening. So to measure this precisely, what we have to use is the photoluminescence, because as I said, the bright spins will lose their photoluminescence when we are scanning across a degeneracy. So now what we built in our lab is a system which is composed of a fixed magnetic field in the presence of an electromagnet that we use to scan the B field, and then therefore we can tune both the direction and the amplitude of the total magnetic field. So when we run again optically detected magnetic resonances on the 0 to -1 transition, we see these 3 ODMR. So I should say these are experiments that are done with a diamond that is not levitating at the moment. So these 3 ODMRs, they show that there are degeneracies, right? We should expect 4 features, and we see only 3, 2, and 3, meaning that at this point we should have a drop of the photoluminescence, and this is really what we observe in our lab. So we take a micro diamond, we scan the B field using this electromagnet, and we see these drops, which all the time correspond directly to a degeneracy. And as I said, degeneracy increases the number of the density of resonant atoms, and so that's no surprise that this dipolar interaction leads to a drop of photoluminescence. All right, so this was the first part, talking about the dipolar relaxation. And now I would like to move to the second part of this second section, which is about our understanding of this diamond paramagnetic susceptibility. So in the first part, I discussed experiments where we polarize the spins to the ground state. We bring a microwave to magnetize the NV centers. What I would like to show you now is another kind of effect, which is when the NV centers become magnetized without microwave. Okay, so this takes place under significant magnetic field when the magnetic field reaches about 200 Gauss or up to 500 Gauss. And if the B field is at an angle with respect to the NV center, what will happen is that the NV center's magnetic state are going to be mixed. So this is something I already discussed in my previous slides. For instance, the ground state G is a coherent superposition of the other states. Meaning that when we apply a laser light, even though we polarize in the G state, the expectation value of the SX component is not going to be 0 anymore, right? So again, the transverse part of the B field induces a magnetic moment along the X direction. We have a magnetic field that is pointing along the Z direction. Therefore, we are expecting a magnetic torque in the Y direction, simply by shining laser light and by bringing a magnetic field at an angle with respect to the NV axis. So it is really, there's a strong analogy between what we expect to be happening here and the magnetocrystalline anisotropy that takes place in some materials. In most materials, actually, you have this anisotropy, and you can, write down the induced magnetization and relate it to the external B field via this linear susceptibility, which is in this case a tensor. And by writing down, it's really a strongly anisotropic material because the induced magnetization is only along the X or Y direction. And so the calculation is fairly simple. We end up with crystalline anisotropy of about 10 to the minus 3. So the susceptibility of our paramagnet is 2 orders of magnitude larger than the diamagnetism of the orbital the electrons from the carbon atoms, right? So it's quite a significant effect in principle. We should be able to observe it experimentally. The problem when we thought about this experiment for quite a bit, but it was tough to observe because of the fact that we have 4 NV center orientations. So if we include, the previous slide was discussing the paramagnetism and the corresponding susceptibility in the presence of a single class, which contains 10 to the 9 atoms. If we consider now 4 NV orientations, then this single class susceptibility drops to a 10 to the minus 5, or 5, 10 to the minus 5. So we have a factor of 20 reduction in the magnetic susceptibility, which means that it's now going to be really competing with the diamagnetism and with even the pole trap restoring torque. And that's the consequence of quasi-rotational invariance, if you want. So all the spins exert a torque that in total reduces the spin torque. And this is where cross-relaxation come in. It turns out that if we are able then to tune the B field in a way that 2 particular classes of NVs cross-relax due to the dipolar interactions, then it brings back the single spin torque amplitude. Because it breaks this rotational invariance that I just presented, we can really have a larger spin torque and get susceptibilities in a range of 10 to the minus 3. So this is where we use this resonant dipolar interaction to enhance the magnetic susceptibility. So experimentally, to try and observe that, it's actually now quite straightforward. We really run a magnetic detected magnetic resonance, a mechanically detected magnetic resonance. So we don't look at the photoluminescence now. We look at the motion of the diamond as we sweep a microwave to try and observe this degeneracy. Okay, so we run in this particular case 3 different NDMR scans, and we tune the B field to try and observe the degeneracy. And we see that at 17 Gauss, there's a point where 2 peaks merge, which in principle should correspond to a crossing of a plane where degeneracy between the classes 3 and 4 is occurring. So looking at the photoluminescence, we see that when we reach about 17 Gauss, there is a reduction. This is an experiment, of course, that now is done when the diamonds are levitating, as opposed to what I showed before, hence the reduction of the signal-to-noise ratio. But here we see really that there's a reduction of the photoluminescence due to the fact that we have dipolar enhanced cross-relaxation. And at the bottom here, you see a theoretical prediction. And now if we do the experiment by looking at the reflected field of the diamond surface, what we observe is that when we scan the B field at exactly about 17 Gauss, we see again a change in the reflected light intensity on the photodiode. And this confirms the hypothesis I just discussed earlier, which is that when we cross a degeneracy, we recover the full magnetic susceptibility, which enables then the diamond to turn and change the intensity of the reflected field on the photodiode. So we really use this dipolar interaction to enhance the spin torque, and we are thinking now about using this effect under vacuum to also induce spin cooling, because you see we have this very sharp feature now due to dipolar coupling, which in principle, if we tune the B field to the blue or to the left, and if we play with a delay in the same way as we play with a delay on the spin cooling experiment with a microwave, now without microwave, there should also be a significant cooling taking place. We are working on this at the moment. And with this, I'd like to conclude. I presented to you some recent results on this, how we play with the spin and the mechanics to do spin cooling and use the dipolar interaction to enhance the mechanical magnetic susceptibility. And we are thinking about using this dipolar interaction also to detect other paramagnetic species. So using MDMR, scanning B fields, hopefully we should be able to measure P1 centers and other kinds of paramagnetic defects in the diamond or in other crystals. And this is all I wanted to share with you today. Thank you for your attention.
Thank you, Gabriel, for that very impressive and exciting talk. So before we ask questions, I think if everyone can unmute themselves and just thank with a clap, virtual clap. Thank you. So let's begin with questions. So if anyone has any questions, Sophia and Leah, if you can just have a look at YouTube for me. Sugato, please.
So hi Gabriel. Yeah, very interesting talk. Okay, so this new thing about these interacting dipoles. So they are, it's like is it like so when you use the word paramagnet, but their interaction is also playing a role, right? So it's a bit like a ferromagnet also. Is that right? A dipolar version of.
Well, of course, dipolar interactions are the key to observing paramagnetic to ferromagnetic transition. But in our case, we have this huge anisotropy to fight first, because the D parameter is 2.87 gigahertz, and the dipolar interaction strength is a few hundreds of kilohertz only. So we have a few orders of magnitude to play with before we can think about entering a ferromagnetic regime. And then we'd have to worry about how the intersystem crossing in excited state enables to prepare a magnetic state in a ground state. So that's also something that is a severe hurdle. But,
And have you thought of coupling these collective things to translation rather than rotations?
Yeah, we think we've seen effects in the coupling to the center of mass motion, if that's your, but we are. It's hard to distinguish between when we run MDMR, both effects are taking place at the same time. So there's libration and center of mass motion. So we really have to make sure that we can separate the two effects when the diamond moves. And so we are now thinking about going in and do some more sophisticated analysis, but this takes time. So
you're able to differentiate by changing the pressure. I mean,
yeah, of course.
Would that have a different effect on this rotation in the center of mass motion?
Yeah. So what we are trying to, what we think we have observed, we have to confirm that again, but is a force. And so if we go under vacuum, we'd be able to see the center of mass motional peaks, which would move if we have a restoring magnetic force, to changing the magnetic confinement. So, but we could also, there are tricks to play, of course. If we modulate the magnetic force, then of course on the center of mass motion there should be a peak, and it's.
So one quick question I had related to these speckles that you showed in the beginning, right? You were detecting many speckles with your one of the speckles points with your CCD or. So if you were to why not detect a number of them that would give you better resolution and maybe translation and rotation?
Yes, it's something we're investigating at the moment. We're trying to really understanding the full speckle pattern and 2D analysis of images, high-speed camera, trying to. Then this is a route towards discriminating the effect of the center of mass and the libration, of course. It's ongoing.
Thanks.
Ongoing work.
Gavin has a question. Gavin, do you want to ask by chat? Would you want me to read it out?
Yeah, I can ask. Hi, Gabriel. Great talk. Lovely work. So can you say anything about turning off the ion trap to have brief periods of free fall or sorts of different time varying control of the ion trap potential?
To try and do force sensing, for instance, or to see if there was a way to start making matter wave interferometry or things like this. I guess this would be. We have not played too much with this. We've done it once, to try and modulate the potential, just to try and see what was happening, but it seems to escape very fast. So we haven't optimized anything. So there are, our injection method is quite crude, and there are many diamonds that get stuck on the trap at the same time as when we have this levitating diamond in the middle, there are patch charges on the diamond, on the pole trap, which then when we turn off the trap voltage, mean that they will immediately attract the levitating diamond. So that, I guess, so we'd have to first clean up the trap and then do which is difficult. It would be nice if we would be limited only by gravity, but it's really tough.
There's a question from Anupam.
Yeah, so a nice talk, Gabriel. It's very nice. So just wanted to know, so can you measure the diamagnetic induced potential in some way? And especially when you have the transition from paramagnetic ferromagnetic, can you see the difference?
So which transition from para to dia? No, it's in this slide I was comparing only the paramagnetic susceptibility, which is coming from the nitrogen-vacancy centers, to the diamagnetism of the orbital electrons on the carbon atoms. There are 2 orders of magnitude difference, and therefore,
No, so what I'm looking at into your Hamiltonian, there is not. There must be a term which is induced magnetic potential.
Yeah.
And so it's not there, but maybe is there any way you can measure it in your laboratory?
The induced magnetic potential?
Mm-hmm.
Yeah, it's a good question. I mean, it's precisely the difficulty is that if we take 4 NV centers, 4 classes of NV centers, the induced magnetization is very small. And it's on the order of the diamond diamagnetism, as well as being on the order of the pole trap restoring torque. So it's difficult to measure it with under the magnetic field values we use at the moment, because of the fact that all the spin torques are competing and give rise to net torque that is very small. So we cannot directly measure it very efficiently, and that's the reason why we resort to this dipolar enhanced interaction, which restores back this susceptibility.
So what you see is that the magnetic susceptibility changes. Usually it's 10 raised to -5 for diamond.
The diamagnetism, yes.
Yeah, but can you make it even weaker? Is there any way you can make it weaker? because you enhance it, I think it can go up to 10 raised to -3 in your case.
To make it sorry.
So this diamagnetic, sorry, the paramagnetic term chi in your.
So yeah, we can. So there are ways to increase it.
But can you? Yeah, is there a ways to decrease it? That would be very, very interesting if you can.
Okay, in order to.
Actually, yeah. So perhaps what he's telling is that if you can subtract the one from the other, the paramagnetic, can you kind of cancel off the diamagnetism in some clever way?
Yeah.
Yeah, this is a good question. So in terms of this comes down to, I guess, being more quantitative and really extract the various. This is really difficult because we don't know the shape of our particle, and the diamagnetism that I was talking about is coming from shape anisotropy. So since we don't know the shape of our particle very well, and we do not know the respective angles between the NV centers and the particle anisotropy, and we don't know the inertia momentum of our particle either, playing quantitatively here is unfortunately very difficult.
So I have one last question. So have you thought about even coating the diamond by, say, I don't know, maybe nickel or something which is slightly heavy element?
Yes.
And to see how the effective chi would change or would modify? Or
yes,
can you do this in your laboratory somehow?
It would increase, this does increase the susceptibility, yes. By quite a lot. I mean, we've done experiments where we coated a diamond with 200 nanometer, if I recall well, of a nickel, and we see trapping frequencies or librational frequencies that are really enhanced by an order of magnitude.
I see.
And we are working now on trying to increase the thickness of this nickel layer and trying to investigate whether this can have some interest. Of course, this will increase the librational frequency. At the same time, perhaps there will be effects such as eddy currents and things that would some magnetic noise that would ruin the NV center's coherence time as well. So, but it's a difficult experiment to.
Thanks. Thank you very much. Thanks.
Thank you.
Sorry, let me just check if there's any questions in YouTube. Okay, so as it stands, there's no more further questions. I just want to thanks Gabriel once again for an excellent talk and presentation of really exciting results. I think we've all really enjoyed that. So just another round of applause if everyone's willing, and then but don't leave yet. There is some additional announcements we want to make at the end. So just a round of applause for Gabriel. So bear with me 1 second. I need to share my screen. We want to. I hope you can see this. All right, so just a word for everyone for the coming next year. So we have some big plans. Some of you may already heard, but of course, everyone should be aware we have Ben's lecture series starting on the 11th of January in looking at decoherence in open quantum systems. And you need to, you have to fortunately sign up for the Eventbrite to get this link, just so that we can monitor it better. So this will last a week. Afterwards, we'll start on what is known as a block system now. We'll give a more focused sort of theme and theme-based approach to all the talks that will happen. Oh, what's happened here? Yeah. And these are the blocks that we'll be exploring. Now, next year is a bit, we're still not sure what's going to happen in 2 months' time, but this is the plan. We already have our first block finalized, and that will start on the 27th of January. And of course, we'll send those emails, but I just wanted to share this with you to entice you for next year. So don't forget us. and we look forward to meeting again in the new year. In the meanwhile, everyone should have a great holiday and take a break from screens, maybe.
and just two more things. Sorry,
yes, okay,
sorry everyone. There are two more
please,
things just before we leave. So put a link to survey in the chat. We would be super grateful if you could have a look at the survey. Tell us what you liked, tell us what you didn't like, because we really want to improve these seminars and make sure that we are providing something that is of value to the optomechanics community. So we'd really appreciate this. And then finally, this is the last UniKORN talk for this year, and thank you all for joining us, and it's been really great. But there are actually some other seminar series that will have a few more talks this year. And so Sugata and Anupam, if you just would like to really quickly tell us about your upcoming talk for the end of the year.
So one our seminar is on interference experiments related to gravity using optomechanics or other fields, and there actually the next speaker, Marcus Aspelmeyer, will be next Thursday. Right, we have heard from him now. So if you can, if you would like to join that, and since he also started the UniKORN series, the speaker, we have requested him to say more about the gravity side than the optomechanical perspectives he gave earlier. And then early next year there will be a theory oriented one by Carlo Rovelli that is on 12th January. So these are all supposed to be, so that will be a Tuesday. So our usual date is on a Tuesday, but I think Marcus's will be next Thursday. And that will be the last of this year. And then the first of the next year is probably the one by Carlo.
Fantastic. Thank you so much, Sugata. So I think that's it for today. Thank you everyone for coming.
Bye.
Bye. And if we could just ask Gabriel to stay behind for just 1 minute. All right, let's see. So we had a final thank you in the chat. So basically, Gabriel, we just wanted to thank you